Welcome, everybody in the lecture hall. Welcome the even more numerous people on Zoom. Today we are going to finish what we started last week, which is about theoretical part, as you can see from the image right there, the relational algebra. And then we'll switch back to a practical part where we will learn how to query with SQL, which is the implementation of the relational algebra, actually. So I start with this question right here that I can activate. So which one of the following comments is not a DDL comment? Is it create table, alter table to add a column, insert into, or drop table? So I try to see if I can hide the responses and not show the correct answer, just as a test, and we'll see if there's a way to show them. So let's see if I can click somewhere and what happens when I click somewhere. Where is my mouse? Oh, it's right there. Oh, now I can show the responses like this. And the correct answer was indeed the majority. DDL means, anybody knows DDL, remember? Yes? Data definition language. And what would be the other one? Insert into it's D. Anybody? Yes, correct. Data manipulation language, DML. All right. So that's great. Now let's go to the next one. So I'm giving you a schema. You know that we give a schema in SQL with the create table statement with all the columns and the types and the constraints. And so here I'm giving you create table, my table with A char3, B numeric 5, C date, and D Boolean. Numeric is the same as decimal. So which tuple satisfies these constraints? Which one of the tuples could you not fit in this schema? Take the time to go through the values and the types. Let me show you now the answers that have already been entered so that you can see them. You already have many answers. Very good. So we have a majority for answer number 3. You can still change your answer if you want, but be careful, the majority is not always correct. Okay, and the correct answer is, if I entered it correctly in the system. Oh, yes, that's the correct answer. The fourth one. So let's see one by one why they don't work. So the first tuple, what's wrong with the first tuple? The first record? Yes? That's correct. So here is the number of characters in A, which is limited to 3, as you're saying, and there's 4. So that cannot be the first one. The second one, why can it not be? Yes? Exactly, attribute E, I'm repeating for the people on Zoom to hear, attribute E is not defined in the schema, so it breaks relational integrity in a way that's not allowed because schema is always closed in SQL, so you cannot just add more values like that. So the second one is incorrect. For the third one, it might work if you try to insert it, but you're going to lose information. Do you see where? You want me to tell you? So the third one is B, because B has 4 digits before the decimal period and 1 digit after the period. But when we say numeric 5 or decimal 5, we mean a precision of 5 digits, but they have to be before the period. If you do not give a scale, then it's an integer, right? So it means that it would store it might fit it, but it would be as 0, 1, 3, 2, 4, and the 0.5 is lost, right? Because it only, or 3 to 5 if you round, and then the precision after the decimal period is lost. Who agrees with me? Okay, yes, there's a question. Do you mean like, for example, with numeric 5, 1, to pass a scale of 1 to allow for the decimal point? Yes, absolutely. Then you would say B numeric 5, 1, 5, 1, and then that would mean 4 before the decimal period and 1 after the decimal period, right? But if you do not add any scale, so the second parameter of numeric or decimal, then it's an integer, and all the precision will be before the decimal points, right? Exactly. By default, the scale is 0. If you do not specify the scale, it is 0. Yeah. Okay. Very good. And the last one is correct. And D comes before C, but we saw that it doesn't matter because it's a map, right? So in a map, there is no order between the attributes. So we don't mind that D comes before C. Okay, so now we can move on to the rest of the materials. So remember that we stopped at the Cartesian product, where I gave you a very big word of warning saying if you try to compute the Cartesian product of a table with 1 billion rows and another table with 1 billion rows, then you're going to end up with quintillions of records, and that's going to crash your computer, right? So I gave you that word of warning. In fact, people rarely do Cartesian products, or at least they would only do Cartesian products followed by some filtering, right? But as we will see, this is actually a join, right? So a Cartesian product might typically be part of a query, but that's not going to be the output of the query to not crash the machine. Okay, so this is why we have joins. And joins use this beautiful symbol that is like a cross, but with the 2 additional vertical bars. So R joined on S. And here we see that we join, but we prepend the name of the table to disambiguate right here, just for the purpose of computing. And then you see that the difference with the Cartesian product is that I'm only taking the green ones, the ones that are highlighted in green, because they match. We have foo1, you agree? Foo1 matches and bar2 matches. Who sees that? Right? Do you agree? Yeah, it's enough to say yes with your head, and I know you're following, right? So they have to match. We cannot take any combination. We really have to take the combination here. I'm not seeing myself. Here, the foo1 must match with foo1, and the other one, what did I do here? No, only B, sorry. I'm the one, so let me rewind. Natural join means you look for the attributes that they have in common. The attribute that they have in common is B, and so B must match. It means that since you have B equals 1 right here, it only matches with that record right here. And since you have B equals 2 right here, it only matches with this record right here. So you only have the combination with the first record and the first record that matches, and the combination with the second record and the second record that matches. These combinations here do not match. 1 is not 2, 1 is not 3, 2 is not 1, and 2 is not 3. So we only keep this one and this one, which gives us this. Who agrees now? Right? All based on the attributes that the two tables have in common, right? So A and C appear only in R, D appears only in S, but B appears in both. So this is why we call it a natural join, right? On the attributes that match. Okay, so we call it R join S. Okay, and by the way, that's internal, the R.B, S.B. Actually, what we do then is we combine them because they're the same anyway, right? So we only keep one single B in the output. It's the same B that comes from here and that comes from there, right? So this here is the result of R joins S. Who is with me? Right? Okay. Now, there's, like many things actually that we see in the relational algebra and in the query language, you might try to push things to their limits and try things that might be a bit unusual. For example, what happens if somebody wants to compute the natural joins of two tables, but they don't have any attributes in common, right? So you can try, you can do it, but it's not a good idea because this is not what the natural join was designed for. So technically, if you have a natural join but the domains, the domains don't match, for example, then an integer will never be the same as a Boolean, and then you will have an empty table, right? But that's not something people are going to do, right? If you do a natural join, then you normally do it when the domains also match. Likewise, what if the tables do not have any attributes in common? So here it's B integer, B Boolean do not match. Here it's that there's no attribute in common, right? ABC does not overlap with DE. So you see the thing here, then technically it's the whole Cartesian product. That's for the mathematicians because when you're saying that all attributes have to match, when you say all of an empty set, that's called the universal quantification on an empty set, and it's always true. So it means that it's going to preserve all the combinations. But again, I wrote in very big letters, better avoid and better avoid because you should not be doing this, right? It's only for mathematicians that might like to take formally even to the corner cases. But in this class, we should avoid that. We are not going to do anything like this, right? So we only take a natural join when first the attributes overlap. So there are attributes in common on both sides. And for these attributes that overlap, the domains also match, like here. This is a natural join as we will do it. Okay? So it's that's just another picture that shows how the join works. So really the idea is that you have a table here, a table here, there. You have the attributes that overlap, and then you only match those. A would match with this and with this, and B would match with this. You get 3. Now, there might be cases in which the attributes are not the same, those that you want to match. So you might want to say explicitly what combinations you retain in your join. That's called the theta join for some reason. And the difference with a natural join is that you specify explicitly the predicates on which you join. So here we say A must be equal to D, right? A must be equal to D. That's the difference with the former one that didn't have anything because it was natural. So let's do it together. A equals D. Where is A? So A is right here, and D is right there. So these are the ones that should match. So now I'm going to take all the combinations. There's 2 here and 3 here, so there's 6 combinations, and you tell me they match, they don't match. So let's start with this one and this one. Do they match? You can say yes or no with your head. So do they match? Yes, they do. Do they match? No, they don't. Do they match? No, they don't. Sorry, yes, they do. Yes, they do. Foo and foo. Now let's take this one and this one. Do they match? They do not, right? Foo and bar. This one and this one? Yes, they do. And this one and this one? No, they don't. So how many did we say yes to? 3 of them, right? So out of these 6, only these three survive because A and D are the same. You see, foo, 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 and bar, bar. And we only keep those that actually match. So you see, it's like a natural join, except that we, the user, specify when we keep the combinations, while in the natural join, you keep the combinations if the overlapping attributes match. Who is with me on the theta join? Very good. Okay. As it turns out, you can rewrite a theta join with other operators. Could anybody guess how I could rewrite it? Let me say you have the Cartesian product, you have projection, you have selection, so union, intersection, like all of that. Could you give me an equivalent formula? Imagine that I didn't have the join on A equals D. How could I compute it from other operators? Let me refine a bit. I give you the Cartesian product and the selection. Can anybody write this with the Cartesian product and the selection, sigma? An equivalent formula. Anybody on Zoom? Okay. Let's look at the visual again. Do you see that when I showed you the theta join, we computed a Cartesian product in our minds because we look at all combinations. So it's first a Cartesian product, followed by, what is it called when I specifically pick the ones that have A equals D? What is it called in the relational algebra? When I select specific rows, it's called the selection, right? Remember? So basically, it means that I can rewrite it in this way, that R joined, theta joined with S with A equals D is the same thing as the Cartesian product followed by a selection, right? And a Cartesian product followed by the selection is going to be giving output that's not too big. Now we have other inequalities, and now it's just like math, right? You have all of these operators, and you can derive mini theorems. For example, the intersection of two tables, R and S, turns out to be equal as R, where you remove everything in R that's not in S, right? If you think a little bit about it, that's what the intersection is, right? Who is with me? Right, perfect. Then if I give you two relations and I give you their schemas, R has attributes A and B, S has attribute A and C, can anybody give me how we can write the join between R and S, knowing that you need to be careful, it's a natural join that would be based on A. And you might have to rename columns to be able to write the formulas. Does anybody have any ideas? It's actually very similar to the animation that I did earlier, where we duplicate, we have R.B and S.B. On Zoom? R.B, S.A, C. Let me look at the written formula. On Zoom? Where is the chat? That's exactly the idea. So we need to basically duplicate R.A and S.A. So of course, that's what PostgreSQL does, but we need to basically rename one of the two, right? So that's basically exactly the idea that you mentioned in Zoom. We basically need to oh, that should be a row here, not a sigma, that should be a row. We rename A to A prime, right? Row A prime. And then we compute the Cartesian product, and you have exactly what you say in Zoom, which is basically A, B, A prime, C. Then we have the selection that only keeps the combination that matched, because it's a natural join, so it's the A and what used to be A on the other side, they must match. Then we project, because it's the join, we need A, B, and C, and A prime, we get rid of it, right? Who agrees with that formula? Right? Just assuming that maybe I can actually, to be absolutely clear, because I really do not want any confusion. So just a minute, because that's very quick to do. I'm just replacing the sigma with a rho because that's a rename. There you go. Now I reproject and no, I need to retake my reshare the screen. That's very strange. It's hanging. I mean, that's the Devo effect. I shouldn't have tried to tamper with the system. Oh. Try again. Otherwise, I'll find a different way to project or restart it. I'll reproject here. Then screen share. Oh, there it is. And I select the one. Full screen. Yes. Now it is working again. So you see, this is the one I changed was right here. I just had a sigma, and that should be a rho. It's a renaming. So we rename A to A prime on S's site. We rename A to A prime. We join. So now we have the schema you said on Zoom with A, B, A prime, C. Then we select those for which A equals A prime, and then we project on A, B, C to get rid of A prime, and we have the join. Perfect. And now the formula is also correct. Okay? And now I'm going to throw plenty of mini theorems, but in the exercises you can look at them. Maybe I can ask you if you have the intuition of them. First, selections commute with each other, meaning that if you do sigma of sigma of sigma of sigma of a table with different predicates, do you agree it commutes? The order in which you select doesn't matter. Who agrees with that? Right? Very good. So the order of the selections does not matter. This is what's called commutativity with operation. They commute. Then selections commute with projections. What I mean is if you do sigma of pi over relation, it's the same as pi of sigma over relation with just one condition, is that the projection does not remove any variables that are used in the predicates. That's the only condition. Basically, if let's say I have a relation that has A, B, and C as my attributes, and I project over AB, and then I take the predicates sigma B greater than 2. Do you agree it's the same as doing it the other way around, of first saying sigma B greater than 2, and then projecting on AB? Do you see it's the same thing? Right? You basically take a few columns and take a few rows, or you take a few rows and then you take a few columns. That's the same thing. Right? Who agrees with that? Right? Okay. Then we have that projections commute with one another. So here it's with the idea that if you project on attributes that don't exist, they are just ignored. So if I say projection to AB followed by projection to AC, which is only going to keep A, it's the same as projection to AC followed by projection to AB, which also retains A. Who agrees? Right? Okay. Then we have that joins also commute. If you do R join S or S join R, it's the same thing. Who has this intuition that the order in which you do the join doesn't matter? Yes, if you raise hands, right? So R join S is the same as S join R. Who agrees the union of two tables is commutative? R union S is the same as S union R. Right? Just follows from the commutativity of unions of sets. Intersection is also commutative, the intersection of two tables. Doesn't matter if you do R intersection S or S intersection R. Who agrees? Okay, that one's intuitive. Now, associativity. Associativity basically means that if you say, let's do it with the union first. It means that A union B and then union C is the same as A union B union C. It basically means you can put the parentheses where you want, right? Either first B union C and then A, union A, or first A union B and then union C. Who agrees it's the same? Right? That's called associative. The intersection is also associative. Who agrees? right? And the joins, do you see they're associative too? So R joins S joins T. It doesn't matter in which order you do it, right? First R join S and then join T, or first S join T and then join R. It's the same. I have here a little asterisk for the purist mathematicians, as I said. The reason the join is associative is the same as when I said the Cartesian product is associative, right? A mathematical purist would say, no, Cartesian products are not associative because of the way they nest. But for databases, when we combine partial functions, we implicitly flatten them. So if I have a Cartesian product on ABC and then D and E, it flattens to ABCDE, right? So there is no, we don't nest the Cartesian products. But that would be only for mathematicians who are picky about these things. Okay, so join union intersections are associative, meaning if you join 10 different tables, it doesn't matter in which combinations you do it. Now, projection distributes over union. What does distributivity mean? I can explain to it with multiplication addition, is when you say that A times B plus C is the same as A times B plus A times C, right? We say that we distribute multiplication over addition. Who remembers that? From primary school or junior high school? I didn't see any raised hand. Who agrees that A times B plus C is the same as A times B plus A times C? Who agrees with that? Right? Awesome. So this is called distributivity. And when I say that projection distribute over union, I mean that if I compute the union of two tables, R and S, and then I project, it's the same as first projecting and then doing the union, right? The result is going to be the same, right? For whom is that intuitive? Some of you? You'll have the exercises, right? So that you can try them out and see, you can take a few examples and see if you convince yourself. Selection distributes over union, intersection and subtraction. So it means that if you take the unions of two tables and then you select based on a certain predicate, it would be the same as if you first select on the two tables independently and then do the union, right? For whom is that intuitive? Okay. It's getting more complex, right? Join distributes over union. It means that if you have R joined with S union T is the same as R joined with S union R joined with T. For whom is that intuitive? Maybe less, right? The more complex it gets, the less intuitive it is. And I have another one. A projection is absorbed by a projection on a smaller subset, meaning that if you project on ABC and then you project on AB and then you project on A, then it's the same as directly projecting onto A, right? For whom is that intuitive? Right, this one maybe even more. Okay, but anyway, these are just meant as mini theorems to basically show you the kind of things that you can do with the relational algebra. You will have exercises on this, so do not worry if it's not intuitive right now, but you can just work on it offline and work the intuition of this. But I need to tell you why it's important, because you might think, okay, why these theorems? Nobody cares about these theorems, but no, people do care. And the reason they do care is because of optimization. Because what's going to happen when you sit in front of your notebook and you type a SQL query in PostgreSQL, maybe your query is not optimal in the way you typed it. It might be written in a way that is correct, but maybe not optimal. Well, PostgreSQL uses that kind of mini theorems to modify your query and rewrite it in a way that is equivalent, thanks to these theorems, but that's going to be faster. So it means that the goal of a system like PostgreSQL is that even if users do not know much about databases and they write queries that might not be efficient, with these theorems, PostgreSQL can still execute them very efficiently, right? An example is, imagine that a user has a table with 1 million rows and another table with 1 million rows, and the user says, I want to make the Cartesian product of these two tables. That would be highly inefficient because we'd have trillions of rows in the resulting table, followed by a selection. But thanks to the mini theorems that we've seen, and in particular the fact that a selection on a Cartesian product is the same as a theta join, Remember that? Then PostgreSQL will figure it out and say, oh, I see, the user is doing this Cartesian product followed by a selection, but I know that this is the same as the theta join, so I'm going to implement a theta join instead. And then you will see that even though it would have generated trillions of rows and crashed the computer in fact does not crash because PostgreSQL was able to rewrite the query in a way that doesn't crash. For whom is that clear, this motivation? Right? That's the magic of a relational database management system. That doesn't work in Python. In Python, if you actually would do this, the computer would crash. But in a relational database management system, the computer does not crash when the engine is able to interpret what you want and do it more efficiently. So this is the beauty of data independence, in fact, to have systems like this. Okay, I wanted to make sure that you know that there's a reason for why it matters that we have this sort of theorems. This is what prevents your computer from crashing. Okay, any questions so far? Who is still with me? Right? Okay, it's Friday morning, right? Almost the end of the week, so we're all a bit tired. Okay, so if this is all good with you, I'll proceed with another Greek letter, this time gamma. We already have rho, we have sigma, we have pi, we have joins and so on. So I continue with gamma. Gamma is for grouping. So here's an example. Imagine I have this table that has these two columns, and you see in column G on the left, you see that the values repeat. I basically have foo at multiple places, right? I have bar at multiple places, and I have foo bar at multiple places. And now the idea is that I would kind of like group them together and aggregate things. And what I mean with this is just conceptually, as an animation, imagine that I just reorder them. That's something you can do in your mind, right? You put them together. It's the same because it's set of maps anyway. Then I kind of want to merge them, right? All the ones that have foo, all the ones that have bar, all the ones that have foo bar, I want to merge them. But what do I do with the values? Well, I can aggregate them. For example, I could take the sum. 19 plus 4 plus 46 gives us 69, 28 plus 265 and so on gives us 677, and 54 plus 3,456 gives us 3,510. Who sees it? Right? That is called an aggregation. Extremely powerful, and this is probably the one thing that in a statistics office or this is the one most important thing that you would do with data, right? You have trillions of records, billions of records. You want to aggregate them to extract high-level information. An example would be you have a table with all the cities in Switzerland, and for every city you have the number of inhabitants. And you also have the canton in which the city is. Then you could aggregate by canton, group by canton, and do the sum of the inhabitants in the cities by canton. And that's pretty much what would correspond to the screen. Who understands this? Right? It's an aggregation. All right, so how can we aggregate? There's many ways. So first I can do the count. I just count the number of values. In that case, that would be 11. Or I can sum these values. 1 plus 2 plus 3 all the way to 10 gives us 55, right? Average gives us 5. Min gives us 0. The max would give us 10. The mode, so here I just modify the mode in statistics is the value that is the most frequent. So if I double the 7 here, then now my mode would be 7, right? So that's statisticians that have this. Then you have the variance. I mean, whatever you can compute basically on a set of values like that. These are just a few ideas, right? And in that example right here, I just showed you with the sum, but in fact, you can use any of the others, right? So now, all of that. You just need to be aware that you can't do it with everything. For example, if you want to compute the sum of the average or variance, then you agree you can only do it with numbers, right? Because you need to be able to sum the number. For the average, you need to be able to divide by the number of numbers, variance, and so on. So this is only for number. We say it has to be cardinal. Min and max would work, of course, with numbers, but you agree that min and max could also work on dates, for example. right? You cannot add dates, but you can see if a date is greater than another date. So you could compute a maximum date or a minimum date, right? You could also do it with strings, right? You can sort the strings in dictionary order, right, lexicographically, and say you have the maximum string or a minimum string if you sort them. That's called ordinal, right? So dates, time, and so on would also work, and of course integer double would work too. And then you have some that are called categorical, where you don't even need to be able to compare them for which is greater, which is smaller. You just need to be able to say it's the same, right? So categorical, then you could do the mode, for example, the most frequent one. Categorical might be a word that you use in machine learning when you have categorical labels, for example, categorical features. Okay, so basically I'm telling you, you can aggregate in a lot of ways, but you can't aggregate anything. Right? It has to make sense what you want to aggregate, right? Okay. And now the formula, the big formula. I told you it's the Greek letter gamma. So here is the gamma. It's right here, right? Here's the gamma. And in the gamma, we need to specify what we group on, and we need to specify what we aggregate on. So you see that here, I'm going to group on country and city. So every time it's the same country and city, it's the same group. You saw I already put the colors, Switzerland, Zurich in yellow, Germany, Berlin in green, and Germany, Frankfurt in blue. And then I'm saying for each one of these groups, I want to sum the prices, aggregate by sum the prices to what I call volume. And I want to count the number of customers because customers, I'm only interested in knowing how many there are and not their IDs. And I'm going to call it non-transactions. So this is what I get. You see, I had 3 groups of distinct country and city. So that gives me 3 records in my results with the 3 groups. And then in volume, I have the sum. So this, for example, is the sum of these 2. And then in here, I have the count. I had 2 here in this group, 2 in this group, and 1 in this group, right? 2 in this group, 2 in this group, and 1 in this group. Who agrees with the results? Right, very good. Now a bit of terminology. Looking at this, country and city are called grouping keys. Grouping keys are the attributes that we use to create our groups, right? And every distinct combination of these attributes gives us one group. So these are called the grouping keys. Then we have the other attributes that are not grouping keys. So these are the non-grouping attributes, if you want to call them that way. Now there is this rule that if you want to involve some of these attributes in the results, you have to aggregate them. You have to. You cannot keep them unaggregated. So it means that for price and or customer, I need to specify an aggregation. For example, I'm saying sum for the price and count for customer. I could have picked any other aggregations that make sense, of course, like max, mean, and so on. So I have to aggregate them. But I'm not saying you have to aggregate all of them in the sense that you could also omit them, right? You could also say just sum of the price and customer, you just ignore it. You just take it out of the picture and don't even put it in the output, right? But if you want to involve them, then you have to aggregate them. You might also aggregate them in different ways. You could do the sum of the prices and also the max of the prices and also the mean of the prices, then you just get different columns in the output, right? So you have to aggregate them. And here, and that's where you have the little arrow, the right arrow here, that's the names of the resulting columns. So the sum of the prices goes into a column called volume, and the count of the customers goes into a column called non-transactions. And I also showed you on the slide what got aggregated to get this. So for example, the sum of this plus this gives us this. And here, it's not the sum, it's the count. Right, so I'm not getting 2 plus 3 here. I'm counting them. That's the first one, the second one, so that's 2 of them, and I'm putting 2 in there. Who is with me? Right, so that is how gamma actually works, and it gives you this result. So grouping also as a conceptual schema. Okay, so now I'm just going to check the time. I still have a few minutes until the break. So I'm basically done introducing the operators. right? Selection, projection, union, intersection, subtraction, renaming columns, renaming relations, Cartesian product, join, theta, join, and grouping, right? That's all of these things that I've shown you. But you agree I did it assuming set of maps, right? Remember that the relational model exists in chocolate, vanilla, and strawberry, right? Sets of maps, bags of maps, and lists of maps. And for now, I had assumed a set of maps. I just wanted to show you that it also works, the relational algebra, if you assume that tables are bags of maps. Remember that bags of maps means you can repeat the same records multiple times. So let's see how this changes if we actually do this. So I have this table. It's a set of records. A bag of records would mean, for example, that I can have bar2 false here and again a second time right there. That's what I mean with bag of records. PostgreSQL allows you to do that. You just need to be careful not to put a primary key, because if you put a primary key, then of course that forces a set of maps. But if you don't specify any primary key, then PostgreSQL will allow you to have multiple times the same records. So let's look at, for example, union queries. Imagine that I take the union of two tables, but it's bags of maps. And now I'm assuming that for a specific value, specific combination, so let's say bar2 false, imagine that I have m times this record in table R, and I have n times this record in table S. If I do the union, how many times will we have this in the resulting union table? With bag semantic, how many times? Anybody? I take a bag, and I take the union of the bags. Yes? 3 times exactly. And the more general formula with m and n? Or in other words, how do you... m plus n exactly. 2 plus 1, m plus n. Absolutely. 2 plus m plus n. Who agrees that we sum them? Right? Very good. It's like I give you a bag of 10 apples and I give you another bag of 5 apples, then I merge them, I take the union, then I have a bag of 15 apples, right? So m plus n. Okay, so that's the union. What about the intersection? What would you think? How many, if I intersect a bag of 10 apples and a bag of 5 apples that all look alike, how many would I have in the intersection intuitively? Yes? In that case, n, absolutely. You probably said n because n is lower than m, right? What if it might be that n is larger than m? What would be the even more general formula? Exactly, the minimum of n and m. That's it. Who agrees? Right? Awesome. And even more complicated, subtraction. What if I want to compute r minus s? Intuitively, what would you say? I have a bag of 10 apples and I want to subtract with a bag of 5 apples, intuitively. On Zoom? Who wants to see the solution directly? Then you have the break. You can rest a little bit. Who wants to see? Okay, let me show you. It's basically m minus n, but you just have to be careful it doesn't go negative because you cannot have a negative number of records. So the max of 0 is just a way of saying if it's negative, we take 0, right? Who agrees with that formula? Right? Very good. Okay. So just checking the time. I think you've deserved a break, right? Because that was very theoretical, a lot of concentration. I just have a few more slides to go after that, and then we go back to a practical thing with SQL. So thank you very much for listening, and I see you in 15 minutes after the break and the coffee.